Hello, everyone. I'd like to welcome everyone to this Intro to Functional Safety brought to you by J.F. Shaw Company Incorporated, along with our Fortress Interlocks principal. J.F. Shaw Company, we are based in Wilmington, Massachusetts, and we have been a certified manufacturer's representative in the Northeast since 1976. We have a team of 4 field sales engineers and an office manager to support our region. We've got some of the leading principals in their technology in their respective markets. Of course, we have our premier channel partners throughout the Northeast to support good opportunity and make sure we maintain good level of delivery and support. And then many of you are our great customer relationships. And today, instead of focusing on product, we are going to be talking more about safety standards, certifications, and levels that we all are running into and that we have experience in the field and that we need to maintain a certain level of production certification. So we have our specialists from Fortress Interlocks on the panel with me. Eve is our safety specialist, and she's going to get into some of the fine details of those levels that we need to meet and different requirements. And we also have a good application support team to get into any type of questions, application specifics, or general concerns that you might be working on with a project. So feel free to offer some questions in the chat. Raise your hand, and then we also have some breakout sessions towards the end to review things. We are going to be a resource for you here locally, but we do have people here that are from all over the globe, but primarily here in the Northeast. Towards the end of the presentation, we'll have some contact info, and if there's any questions, needs, or demos, or et cetera, that you would need from a development or sales support, my team at Shaw Company will be a resource for you. So I'll kick this off to Eve. Welcome everyone and enjoy the presentation.
Thanks very much, Darren. So yeah, I'm Eve. As you can probably tell, I'm not based in Massachusetts. However, I do spend a lot of time looking at American safety standards. As was mentioned, we've got a Q&A function if you want to ask some questions. We've got 2 little breaks for questions, so keep them coming. And if there's any little things you want to check, there's a chat, and there's a few people from Fortress in the background who can help out with any questions on there. So what are we going to look at? What is functional safety? How reliable does your system need to be? What are categories and performance levels, and kind of where do they come from? What are the parameters behind that? How do you calculate those? And hopefully you're looking like the people on the right there, super excited to have a trip through some functional safety. I'll keep it fairly quick, but we will be sending this out after if you want to go back over anything, and we are always happy to answer questions, so go for it. So functional safety is the portion of the safety of the machine and the machine control system which depends on the correct functioning of the safety related parts of the control system. And safety related parts of the control system, which I will shorten to SRPCS throughout this so that I don't lose all function of my words. So it's the part of the control system that is safety related. So to kind of make that a little clearer, because that maybe doesn't make tons of sense, we don't care in functional safety about whether the machine is actually working correctly. We only care that it's remaining safe. So, you know, if you had a paint mixer, we don't really care if the color comes out wrong, but we do care if someone could get trapped inside and it gets turned on. So we're only looking at the safety related parts of the control system. And functional safety is this control system. And so if it were to fail, if something in that were to fail to danger, then the risk goes back to the initial level. So a fixed guard is not functional safety. However, an interlocked access gate would be, because if the safety function is that when you open the gate, the machine shuts down. If part of that system that shuts the machine down when you open the gate fails and fails to danger, then you might as well not have the gate, because as soon as you open it, nothing's happening. So that's kind of the difference there between fixed guards, which aren't some functional safety, and then interlocked or anything that uses the control system, which are. But that should hopefully become more clear. Don't panic. So the SRPCS is made up of 3 main blocks. There might be multiple things in each of these blocks, but the main things are an input, which is operator controls or sensors. So that could be light curtains, that could be non-contacts, that could be really fancy interlocks with all the bells and whistles. There's logic. So that's working out what to do with those inputs and how to control the outputs. That's going to be your PLC or your relays or something like that. And then outputs is whatever's directly enabling or controlling power to the machine actuators that are going to produce that hazardous motion. So again, we don't really care in this about whether it's doing the right thing. We care about the hazardous motion and the hazards that the machine can control. You'll notice that there's like fluid power in here as well, because actually all of this is related not only to electrical power, but also to fluids and mechanical systems. It's all relevant. So first thing to do, so when you're talking about functional safety, you might want to dive straight in with your performance levels and your categories. But actually always the first thing to do, and the most important thing, is a risk assessment. For that, you'd follow ISO 12100 or B110, very similar standards, just ISO versus the US version. You identify the tasks and their associated hazards, and then you calculate the risk by multiplying severity of harm by the probability of occurrence. Hopefully that's not too unfamiliar. And then you take your risks and any of them which are too high to be acceptable, assuming that it's not all super safe to start with, then you work out which risk reductions measures to use. And for that, you follow this hazard control hierarchy, which is in both B110 and 12100. And for that, you start with trying to make it inherently safe by design, so designing out the hazards, making it inherently safe. If you can't do that, then you look at engineering controls. And that's going to be anything kind of like guarding or interlocks or anything that physically separates humans from the hazard and stops them from being able to come into contact with it. And finally, the last thing that you'll do is administrative controls if you really can't reduce the hazard sufficiently by other means. And that's things like lockout tagout, that's things like training, that's things like PPE and things like that. So once you've done that, you've worked out all of your risk reduction measures, then you look at which of those risk reduction measures involve the SRPCS. So remember, not everything does. So fixed guards and things like that, they don't involve any kind of control system, so you don't need to follow those through to the functional safety. But for those that are performed by, do you have safety functions performed by the system, then you define the safety function. And that means that it's kind of just putting it into words what it needs to do. So for example, it could be if the hazard is that you're opening, or the safety function could be that when you open a guard, the machine has to stop. So any time that the guard is open, that could be a safety function. If you needed to open that guard to clear a jam or something, that the safety function would be when the guard is open, the machine must stop. And that's when we start looking at kind of how reliable that system needs to be. But the first thing to look at is how much risk is that specific part reducing. So you can see here you've got your total initial risk. And if we think about, for example, a lathe, you could have it kind of completely open, but with a light curtain in front of it. So that light curtain, when you break it, it stops the machine in time for you to not get caught in it. And that would mean that the SRPCS is reducing all of that risk from initial risk down to acceptable. And there's always going to be some residual risk, but pretty much all of the risk is being reduced by the SRPCS, in this case, light curtains. However, if you had fixed guarding all around that lathe, you might still have a light curtain behind that fixed guarding that maybe stops you catching your finger. but really that's all that's going to happen. Then in which case other risk reduction measures are reducing most of it, and then there's a little bit left to get below acceptable risk, and that's what the SRPCS is doing. So we'll come back to it, but just kind of to have in your mind that you can combine it with other things, and then you're not having to reduce as much with that SRPCS. The system might be the same, but it maybe doesn't have to be as reliable. But we'll come back to that in just a second. First, we get a little sidetrack through safety standards, which is where I spend a lot of my time. If you're talking about functional safety, you may have come across 13849, and this is where performance levels and categories come up. You also may have heard of IEC 62061 or safety integrity levels, and that's basically the electrical kind of sister of 13849. 13849 covers kind of everything, and that's the ISO standard. IEC is the electrical and electronic sister organization to ISO, if you haven't come across it before. And then ANSI, that's the American National Standards Institute. They have their own, which would be B11.26. It's really a guide of how to use 13849. So it works really well. It gives you loads more examples. It goes into lots more detail than 13849. It also introduces control reliability, which I'll mention a little later. So those are the standards. But now back to actually kind of something a bit practical. We talked about how much risk that system is reducing, that safety related part of the system, how much risk that's reducing. And that's where these graphs come in, which you may have or may not have seen before. The one on the left is for categories and is a bit more complicated. So we'll look at this one on the right, which is explaining what the required performance level is for your system. So if we go back to that lathe example, if it's reducing all of the risk, so you could have some serious injuries if something were to break. So you follow this through, you go, is it severity of injury? Is it slight or is it serious? I'd say it's serious. Irreversible injury is pretty possible. Frequency, seldom or frequent. So it's probably frequent if you're using it a lot. And then possibility of avoiding the harm, is it possible or is it scarcely possible? Well, maybe it is possible under specific conditions. You can try not to get caught in it. So in that case, this would come out as performance level D is your required performance level. However, if you were to have it not reducing that much risk, if you had that fixed guarding, if the worst that could happen is you could catch the end of your finger, then I'd say that it's a slight injury, probably still frequent exposure, and you can certainly get away from it if there's not much reason you've been there. So in that case, you'd only need PLB. And so it's important to realize that for kind of the same application, you could need different performance levels depending on what else you're using and what other risk reduction measures are there. This one with categories is similar, but they just kind of say it's possible with more. So open it's over-designed, it's more than you need. The big one is what you should probably go for, and the little one is you'd have to add in more risk reduction with that. So we talked about performance levels, and that's probably the key thing in this, is performance levels and kind of what do they mean. So they come from the probability of dangerous failure. So that table here, so you've got your performance levels, they're rated A through E, and they each correspond to the probability of dangerous failure per hour. So it's a tangible number of how many dangerous failures you are meant to get, you are likely to get per hour of, and so you can obviously see these are pretty tiny numbers, which is positive if you're talking about safety things and how often they're going to fail to danger. And with performance level E, they're very, very, very tiny numbers. Performance level A, they're still pretty tiny, but slightly more likely to have a dangerous failure. And then what we're going to go through for most of the rest of this is actually how do you calculate a performance level? Where do they come from? How do you know what performance level you've got. So obviously we've just looked at how you know what performance level you need for a situation and how you tell that, but then how do you know, how do you actually calculate what the performance level is? So the first way, which is kind of the simplest but maybe the most limited, so the simplest way is just to combine the performance levels of the components. So if you know the performance levels of all of your components, you've maybe got an input, a logic, and an output. If, for example, all three of these were performance level E, you'd look at this and you'd say the lowest performance level, PL low, is E. You've got fewer than or equal to 3 of them, so therefore you can achieve performance level E. However, if, for example, this one of your components, so if this component in the middle was performance level C, your performance level low is C, and you have less than and equal to 2 of the lowest ones. So you could get performance level C if only one component was C. If all 3 were C, then your low would be C, you would have more than 2, and therefore you'd be limited just to B. So yeah, that's kind of the easiest, but maybe the most limited way. And I'm just going to check if anyone's got any questions on kind of what we've covered so far. I know I'm going quite quickly, but I don't want to waste tons of time. So I think Malcolm is around with any questions.
Yes, I am here, and I'm in Boston, but not the Boston that everyone else is probably in at this moment. So yeah, we have a question here. I think this relates to your last slide as well, Eve. Why can't you just combine component PLs for all cases?
Okay.
Back to that.
Yeah, so if I just flick back to that slide before. So kind of as you see, as soon as you've got more than a couple of components, you start to be limited to really quite low PLs. So if you did need, for example, PLE and you need it, but you had more than 3 components or something, then you would be limited to D from this system. It's possible if you calculate it properly with all of the parameters that we'll go through in a minute, that you are able to get that higher PL. So it just means you're often restricted to a lower PL than maybe is necessary. And also you obviously have to know the PLs to start with. So we're going to go kind of from first principles in the second half of this to hopefully explain that.
I think that does answer that. There are 1 or 2 more coming in, but we will have time at the end. We just wanted to put a break in there because that normally gets people asking questions. So there's a few coming in. We'll save those right to the end. So I'll let you carry on, Eve.
Okay. So the next way that we're going to look at is kind of, as I like to call it, from first principles. It's looking at the parameters behind how you would calculate the performance level. And it all comes back to this graph. Don't worry, this is just to introduce it, and then it will come back at the end once it all makes perfect sense. So just to explain how it works, there's performance levels down here. So A through E. Across the bottom, you've got categories, which again, you might have heard of, and we'll go into a bit more detail on what those mean. So you've got Cat B, 1, 2, 3, and 4. You've also got this thing called DC, which is Diagnostic Coverage, which can either be none, low, medium, or high. And then these colors are MTTFD, which again can be low, medium, or high. And as you can see, so for example, here you've got Cat 3, DC, medium, high MTTFD, and you would get performance level E. And then up here, if you had MTTFD low, Cat 2, DC, medium, up here you'd be PLB. And this is how you use this chart, but I'm going to explain all of these parameters and hopefully it will make a ton more sense and hopefully explain kind of why these things are the way they are. So the 4 things we mentioned, or 3 things we mentioned, and then 1 bonus one. Category architecture. So that's the way the system's laid out, and it's basically saying, is it single or dual channel, and is there testing between those channels and checking. MTTFD, mean time to dangerous failure. How likely is a dangerous fault to happen? So mean time to dangerous failure, as it sounds, how long is it most likely to be until there's a dangerous failure in that system? And then related to that is your diagnostic coverage. So if a dangerous fault happens, how likely is it to be detected? And as you can see, that those kind of almost work together. If your MTTFD is very high, then maybe your diagnostic coverage may not need to be as high, because if there's no very, very unlikely to have a fault at all, you maybe don't need to detect it. Whereas if you're likely to have faults, you have a low MTTFD, you may need a higher diagnostic coverage to detect those faults if they're happening more frequently. And then this final one, common cause failure, the reason it's not on that chart is because it's basically a pass-fail, and it's how likely is it that two things will fail due to the same cause. So I'll go into a bit more detail on that, but it's basically making sure you're designing your system that if it's going to get wet, everything's not going to break as soon as it gets wet, because then everything will fail at the same time due to the same thing. But I'll explain it in a bit more detail. So, category architectures. It's the architecture of the system, and the maximum reliability of the system is limited by the architecture. So they're kind of a fundamental part of the performance levels. And as I said, it's kind of single or dual channel, but these single channel ones, there's a distinction between them. So there's category B, and that pretty much, it's the basic one. It says design all the components in accordance with relevant standards, and that it can withstand expected influences. So for example, we've got this picture here. This isn't a category B system, but for example, if it was, it's a very wet environment, and so you need everything in full stainless steel. You can see everything's rusting. It's very harsh environment. You've got to consider that for category B. And then that category B kind of follows through everything. Everything has that requirements of B. Category 1, you also then have well-tried components and safety principles and a high MTTFD. So with that, it's single channel. So if something fails, if one thing fails, you're going to lose the whole thing. But the point with category 1 is that it's well-tried components, well-tried safety principles, very high reliability components. So although if something breaks, the whole thing fails, it's not very likely to, because everything is very well tried and reliable in itself. That's the idea with category 1. Category 2, it's the same requirements as B, and you've still got those well tried safety principles, but you also test the safety function at suitable intervals as well. So if there's faults in between those tests, then you can still lose that safety function. But you should ideally be testing it at every time it's used. So kind of just before it does its thing, check that it's working. And ideally, if you detect a fault, then it should go to a safe state. It can go to just give a warning instead of going to safe state, but in that case, you would always be limited to PLC at the highest. So those are single channel. As you can see, kind of gets more and more reliable between B and 1, and then that addition of checking for category 2. And then category 3 and 4, these are the dual channel categories. They both have kind of the same layout of you've got 2 of everything, dual channel, 2 of everything. With category 3, the safety function is always going to be performed even if one thing has a fault. That's because if this input failed, you've got another input here, and then you check between them and you'd realize there's a problem because they wouldn't be registering the same. However, if 2 things failed, so if both inputs failed before you noticed that one of them had failed, then that could be a serious problem and you could lose your safety function. Which is why for category 3, when reasonably practicable, a single fault is detected at or before the next time the safety function is required, which would stop that becoming a problem. So you'd know there's a fault before it becomes a problem that something else could fail. Category 4 is very, very similar, but pretty much it's that zero tolerance policy of it has to always be able to perform with a single fault as category 3, but also you must detect all faults. That's kind of, it just must detect all faults in time to prevent loss of safety function. So that's taking into account that possible accumulation of faults. and you should never be able to lose that safety function. So those are the categories. The next one on that list was MTTFD, how long before something fails. And this is put into these categories of low, medium and high, 3 to 10 years, 10 to 30 years, 30 to 100 years. Category 4 actually goes up to 2,500 years as high, which is kind of something to make the maths work in the background. But yeah. And we may not have any evidence of things lasting up to 2,500 years, but we do have some evidence of things lasting pretty long times in the field. And things that you can use to calculate this: manufacturer's data. Safety products will almost always come with that manufacturer's data. I'll explain on the next slide what that looks like, because they'd really usually give you the B10D, but don't panic yet. If it's not from the manufacturers, you can get it from annexes in 13849, and the very last resort is to just choose 10 years, but it's very much a last resort. So as I said, manufacturers often give you the B10D, which is the number of cycles until 10% of the components in a test fail to danger. Because the interesting thing about MTTFD is it's the mean time to dangerous failure kind of in absolute terms almost. So if you're only using it once a year, it's probably not going to fail for years and years and years, because the likelihood of it failing at each one of those cycles is probably pretty low. And then even if you're, even if it fails every 20 times, if you're using it once a year, that's 20 years. Whereas if it fails every 100 times, but you're using it 100 times a day, then actually that's going to fail sooner. So your MTTFD would be lower. So the B10D is what will be provided by the manufacturer, and that's cycles to failure. And then you can do this calculation with number of annual operations and timesing it by 0.1, and then you get your MTTFD. To put it into the channel, so that's for each component, you sum the reciprocals to put it as the whole channel. And if it's dual channel, then you can either just take the lowest one of the two channels, or you can do a fancy calculation to even that out. But you shouldn't often need to go into quite that much detail. Yeah, so then diagnostic coverage. You've just worked out how long it's likely to be in kind of real time until you get a failure. But what are you going to do if you do get a failure? Are you going to notice that you've had a failure? So these ranges, again, they're classified as none, low, medium, and high. And it's the ratio of the rate of detected dangerous failures to the rate of total dangerous failures. So this 99% is you are catching every single dangerous failure every time. So that's that cat 4, where you must catch every single dangerous failure. And then anything lower goes into there. And again, you can get this from manufacturer's data. If you can't get it from manufacturer's data for the components, then you could carry out a full FMEA. It's a lot of work, and sometimes it is necessary, sometimes it's not. But you can also get estimates, again, from 13849 has estimates in the annexes and kind of means of, you know, depending how frequently you're looking for faults and how you're doing it, it will give you an estimate of what that range should be. So that's diagnostic coverage. And then that final one that I mentioned was this common cause failure. So it's basically, I've put these up here. It's basically a test. You get these points on the right for meeting the requirements on the left. And if you score 65 out of 100 or more, then you pass. And if you fail, then you fail. So you have to get at least 65 or more, otherwise you have to redesign your system. And the things that this is looking for, as I said, is, you know, is it going to withstand the conditions? Is it, are you going to break all the cables at once if someone trips over them? If you've got two crappy plastic interlocks on a door so that you meet your redundancy, but the first time you slam that door, they both snap, that would fail you for common cause failure, because it's not going to, two things are going to fail due to the same thing at the same time. So now we come back to this. And hopefully, having done a very whistle-stop tour through all of those parameters, it kind of makes a bit more sense. So starting with category 4, as we said, the diagnostic coverage always has to be high, and the MTTFD always has to be high to meet category 4. And therefore, if it's category 4, it's always PLE. And that's kind of the nice, simple one that basically by definition, that's the case. However, as soon as you're down in category 3, you have the option for low or medium diagnostic coverage. Remember, if diagnostic coverage was high, then you'd automatically be category 4 because of the way they're defined. So you've got low or medium. But if you had a low MTTFD, you actually could be down in PLB or even PLA if you had a low diagnostic coverage. Whereas you could have PLC with Cat 1. So I think it's just worth noting that the categories themselves are not kind of linear in terms of getting better. You can have a category 1 that is more reliable than a category 3. It depends on the other parameters as well. Category B, you're unlikely to get a particularly good PL, but other than that, you can kind of get this range with all of them depending on the different parameters. So other ways of calculating it, you can use software. So if you're combining certified components with known PLs and known PFHDs, then you can actually just add them together to get that total PFHD. And that's the way that a lot of the software systems, so Systema, for example, would do that. And you can usually download from, well, certainly our website, you can download that information directly. And I think most safety component manufacturers have that function and just kind of input them directly and do all of that stuff through some nice software. But it's always nice to know where they come from, even if you are using the software. Safety integrity levels is something we get asked about a lot and what the difference is. And in reality, they map directly onto performance levels. So they're from the electrical standard, but they do map directly onto performance levels. So it's kind of easiest for me to say here that work out your PL and you can know what your SIL is. Pretty much it's worked out in a very, very similar way in 61508, but they just call things differently because they were made by different, the standards were made by different committees, but they do exactly the same thing. The next one is control reliability, which I mentioned right at the beginning, is in B11.26. And it's actually really interesting because it's been introduced in the B11 standards. And it's nice because it gives it in words as to how you should make your system control reliable. But unfortunately, writing it in words makes it kind of difficult to know if your system really meets it. So handily, they say here in the explanatory notes that if you meet category 3 or 4 and or performance level D or E, then that counts. So if something needs to be control reliable, this is your best bet, Cat 3 or 4 or performance level D or E. And then you know that you've definitely met those conditions. And then finally, I wanted to mention ANSI R15.06 in case that's something you've come across. And interestingly in this, again, written by a different committee, so kind of, they always have slightly different ways of putting things, but pretty much they think that you should go for Cat 3 and PLD and SIL 2, which kind of all sort of line up together, and that will be sufficient, but you should still do a risk assessment and you should still decide. So if your risk assessment determines otherwise, you can still not do that, but if in doubt, go for PLD is kind of their thing on that. So if you've met your PLR, what do you do next? There's kind of a lot that you need to do, and actually the documentation and validation is almost the most important step to prove why you made the decisions you did, which faults you've considered, which faults you've excluded, and how you're proving that things are well tried, proving that you've looked at relevant legislation. And then finally, the final thing that people sometimes forget to do, but is really important, is test the system. Make sure it does what you've said it's going to do, what you expect it to do. So that's kind of it. I now just want to give you one quick example that will hopefully explain some stuff that we get asked a lot, which is how do you meet PLE with only one interlock? Because if you're trying to hit dual channel architecture, don't you need two of everything? Well, no, is the short answer. You need the architecture, but actually inside here, for example, you've got two separate things. It's dual channel inside, it's monitoring for faults and checking between the channels. Inside, it's as is this interlock inside, it's got all of the electronics and switches are duplicated and checking with each other. Here you've got two contactors, they're monitored, each of them, but you kind of need that second one in case if this gets welded open, then you need another one to be able to close the system to keep it safe. And then the big one that we do get asked about a lot is there's very clearly only one actuator and head here. And in this case, what we've done is that fault has been excluded. So the potential fault of the actuator breaking or the element in the head breaking has been excluded from being considered because it's so much stronger than it needs to be. You know, the entire gate will have broken before this is ever going to come apart when it shouldn't. And so for that, you can then exclude that fault and assume that it is so unlikely to happen that you don't need to consider it. And for our case, we have that approved by a third party because we don't just want you to take our word for it, but kind of trust that third party approval. And so, yeah, that's how you can achieve PLE with only one interlock. And that is the end of my rambling for now. I just wanted to quickly mention that there is a machinery safety poster which we have produced, and if you contact your local reps, we can get those sent out to you if you'd like a copy. And with that, I am going to see if anyone's asked any questions.
Yes, Eve, we have a few questions, but you get to have a drink while we bring our technical director, Rob Johnson, online as well. So if you are there, Rob.
I'm about, Mark, yes. Hi there, everyone.
So I've got a question here that I think is one for you. Where does a single channel modulated signal lie? Is it within a single channel architecture with a high likelihood of detection, or is it more like a dual channel architecture?
Yeah, so might need a bit more detail to be absolutely sure what's meant there, but to me that sounds like a category 2. So absolutely there's a likelihood of detection of faults there. It'll be checking, but as only a single channel, then it wouldn't be able to carry out the safety function and stop the machine if there was actually a fault on that channel. So we could have a test, we have testing there, we could have an output to warn the system, identify that that's happened, but it doesn't have that second channel to stop the machine. There might be sort of, if it's a slightly different approach and maybe we're using a data connection, like SIP safety or ProfiSafe, then you can actually have redundancy within the data. But if we're just talking through a standard OSSD type output and you've just got a single, I would say that's a category 2 single architecture, but with some fault detection.
Excellent, thank you. I think this question, it was made for me. I've answered it on quite a few occasions over in Europe recently. How can a single tong meet PLE, which relates to Eve's last slide, where we were showing just a single interlock in a performance level E application. We use fault exclusion primarily on the metal components, the tong itself. So you could literally hang a car off one of our tongs. At the moment, 13849, which is really where this comes from, where you need to look it up, is ambiguous. And that's going to be corrected in the interlocking standard that will be released in the course of the next couple of years. The latest revision of ISO 14119 will lay very clear criteria around how you use fault exclusion on mechanical components. So hopefully that answers that question. Eve, I think we're back over to you.
Yep.
The mixing process, what's the recommended way to provide safeguards for access? I'm guessing that's talking about delays, I suspect.
Sorry, can you repeat that? I think you slightly dropped out.
For mixing processes, what's the recommended way to provide safeguards for access? And I think that relates to delays, I suspect.
Yes, so with mixing things, it's often the case that just having a simple interlock on its own without guard locking is not going to provide enough, because often taking the power off doesn't immediately make it safe. So with mixing, you'd usually want guard locking or a time delay function. So guard locking would be having a solenoid in your lock on the gate, and then you'd request entry, the machine will be shut down, and once it receives a signal that it's safe to enter, whether that signal comes from a timer running down or back EMF or something like that, and then it will only allow entry once it's actually, the hazard is ceased completely. Is that what we think we're looking for?
Yes, I think that's it. I've got a question here. I'm not sure whether this is for you or for Rob. Does the reset method affect the PL or category?
I'm happy to take that one. So the reset method's not typically mentioned. You might want to look at 14.118, which talks about an expected restart for the reset. So there'll be typically things in there that suggest it's a really bad idea for the machine to restart just if somebody happens to push a gate 2 behind you. And also there's some chunks about the fault detection. So although it's not specific to a category, a lot of the time if there's a fault being found, it must be cleared and the system will recheck itself before the system resets. So you'll often find that in order to meet category 3 or category 4, the products will require a separate manual reset as opposed to the automatic reset chunk.
Excellent, thank you. We're going to do one more question, then we're going to move to our quick pop quiz. And we do have a prize. We have several prizes, actually, I suspect. So we'll just get through this last question. Where are we with that? What safeguarding can be used for high temperature applications above the rating of typical safety products?
I can probably jump in on that, but happy to have anyone else. I think it's an interesting one because electronic components often have an upper limit where they start to go a bit funny or just melt completely. And actually, we often recommend trapped key, which is purely mechanical, at least for the gate locking part of high temperature applications, because they can usually withstand much higher temperatures and can still be used in very high performance level situations, but don't have the issue of having electronics which don't like high temperatures.
Excellent, thank you. And thank you for all those questions. We have one or two more that we'll answer via email. But we'll move on to our famous pop quiz. We've got 3 true or false questions. If you answer those, we suspect most of you are going to get these right. So we also have our kind of tiebreaker question after that. But I'll launch the polling now. And if you want to have a go at answering those 3 questions, hopefully that is coming up on your screens now. The answers to the questions will come out in an email to everyone that attended or registered. So don't worry if you don't see the answers, if we're a bit quick getting that poll out. If you can work your way through that.
And just to clarify, the prize is actually on the screen there. The prize is a Fortress key engraved with your name that we'll contact you about afterwards and get sent out to you. So it's a pretty unique prize that not many people can say they've got. Oh yeah, very. No. And in just a sec, we'll have a tiebreaker question because it looks like a lot of people are getting these questions right.
I'm going to leave it up for another couple of seconds. Still one or two more coming in, quite a few coming in actually, so we might just hang on for a second. I believe Darren Shaw might sing and dance at some point in this presentation, if we leave that up much longer. So that's what they tell me anyway.
I've been
So
known to do such things.
Quite right too. Right, thank you very much for all those who did that. We'll pop the tiebreaker up. If you can answer that in the chat function, that would be great.
Yeah, so here's the tiebreaker. It's what is the maximum value for MTTFD for category 4 systems? And if you jump in the chat, if you think that you know the answer. It was mentioned at some point, probably. I lose track of what I mentioned now. Oh, some people have jumped in there and seem to be.
Maybe we just move on to that last slide.
Yes.
So we'd very much like to thank Darren and his team for hosting us on this webinar. I think it's been really good fun, certainly been good fun for us. Hopefully a learning exercise. I'll hand over to Darren now.
Yes, I mean, in closing, hopefully this was helpful for everyone that attended, and we appreciate it. Keep JF Shaw Company in mind, and more importantly, Fortress Interlocks. They are safety specialists. As you can tell, we are accustomed to guiding and trying to meet the requirements for the applications in the field. You have contact information up on your screen right now. Please jot it down for based on region, and we'll follow up from a Shaw Company standpoint. Thanks for attending, and we'll look forward to hosting another webinar in the future, maybe on a different topic, and we can accomplish something else down the road. Thank you very much.
Thank you, everybody. I'm closing the doors.